Okay, hey everybody, Mr. Bells again. We're going to talk today about section 6.5. And 6.5 deals with something called polar curves. So it's going to be a lot of graphs, things that you'll see that look like this and all kinds of other things. We play around with them a lot. We get to do a lot of artwork in the class, but I'm going to try and do my best to at least give you a synopsis of what's going on right now here. So here we go. So we're going to start off with the first polar curve that we talk about, and that's called a rose curve. And anytime that you have a rose curve, we have some constant right here multiplied by a cosine or a sine. It really doesn't matter which one, and we'll take a look at some of them. And then we're going to change this too. So A cosine B theta. So if you could, go ahead and grab your graphing calculators. Take a look at some of these graphs right now. Let's zoom in on this a little bit for you so you can see it. That looks pretty good. So the first thing we're going to do, go to your mode, and again we're dealing with polars just like we did in that last unit, 6-4. So go to polar mode. When we hit that, R will show up, hit our Y equals, it'll be R now. And basically we're going to put some different stuff in here. So we're going to start off with this one, and we're just going to do cosine of 2 theta. And you can see when you hit the xt theta n button right here, this one right here, that theta will show up. You can see x is for functions, t is for parametrics, theta is for polars, and then n is for sequentials, which we will not get to in this class. I'm going to close parentheses on this, and I'm going to go ahead and hit zoom 6. And you'll see that there's a tiny little thing in here, but it looks like there's 4 little leaves on it. And if I went zoom 2 and enter, zoomed in on it, you would see that it looks just like that. So why does it look like this? And how do we get things to understand why, what it is that it's doing? So here we go. I'm going to zoom 6 back again so that it looks small. And you can see that it really only goes out to the first tick mark on each one of those. And that's what this A is doing right here, because we graphed our cosine 2 theta, that A was just 1. So what I'm going to do is I'm going to go here, and I'm going to insert a number in front, so like a 5. So that's going to take all the values of cosine 2 theta and multiply it by 5, which should indeed simply extend those, what we're going to call them as petals. Because a lot of these things are going to look like flowers. So the petals are going to be length 5. If I do it again and change this to say a 9, you can see that they all go out to length 9. Okay, and that was with 2 theta, but you'll notice with 2 theta there's 1, 2, 3, 4 petals. So what happens? So let's try it with 4 theta. And 1, 2, 3. Look at that. Now we get 8 petals. Like I said, you can do a lot of different things with this. Now, you'll notice that some of the edges are a little jagged, and I know mine's going to graph a little bit faster than some of the other ones. So take a look at it again for our window. Mine's going from 0 to 2 pi. It's going up by 0.13. If I change this 0.13 to say 0.05, 0.05, and hit graph, you'll see that it smooths it out a little bit, makes it a little bit nicer. Whereas if I changed it, instead of 0.05, I made it be, say, 0.5, it would be really choppy. Because again, it's doing it in half increments up to 2 pi. So you really have to think about what's going on with that. And you know, of course, that if you go to your mode and you go to degrees and zoom 6, it'll look the same thing as what it did before, except now your window is going from 0 to 360 with 7.5 degree intervals. So if I put this at, say, 30 degrees, oops, sorry, 0, and put this theta step at 30 degrees, you would see that it looks pretty cool, actually, that design. And again, all it's doing is plotting a point, plotting the next one at 30 degrees, connecting it to the next one, and so on down the line all the way throughout. So if I make that step 15 degrees, you're going to see a little bit different picture going on, and you're like, whoa, that's pretty flippin' cool too. And I think it is. And like I said, we play a lot around with this in class. We're going to do what we can with this. So I'm going to go back here to it. And you can go ahead and keep it in degree mode because I think it helps a little bit. I'm going to put them every, say, 5 degrees right now. That usually gives me a decent picture for what's going on. And then I'm going to go back to my R, and I'm going to go, okay, well, what happens if I put 6 theta? I know that 2 theta gave me 4 petals, and 4 theta gave me 8 petals. So then my goal is, am I going to get 12 out of this thing? And you're going to see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It does. So that's one of the first rules that we'll have on this, is that when we're doing polar curves, that whatever this number is, this is a 2 or a 4 or a 6 or an 8, it's going to give you the double the number of petals. And you're going to ask, well, does that only work for cosine or does it also work for sine? So I'm going to change this to sine. Go ahead and graph, and you'll see now that, hey, sine gave us the same thing. So cosine and sine don't differ in terms of the number of petals. But I've used only even numbers, so now we're going to use an odd number. So let's change this from 6 theta to 3 theta. So this is an odd number. And now I'm going to hit graph. I'm like, oh, wait, what just happened? Odd numbers only give me that exact same number of petals, or at least those are the only visual petals. What will happen is here, if you see this though, and we'll check one more. Let's go ahead and do 5 theta. And hit graph. Okay, so it did work out. So if it's an odd number, it's giving you the exact same number of petals. Evens, doubles, odds are the same. So why does that happen? Or does it really happen? So watch this. Let's go back to 3 and just do 3 theta. And I want you to hit trace. And what we're going to do now is we're going to move it here, and you're going to see as we go around that after I complete one full cycle right here and stop when you get back to the origin, you can look right here in this bottom left hand corner, and it says that I've only gone 180 degrees. Wait, well, I know I graphed it through 360, so what's going on? Oh, look at that. So when I go to 360 for an odd number right here, you can tell that actually what's happening is there is 6 petals. It's just that there's this one that's doubled, and this one that's doubled, and this one that's doubled. So we do get twice the number, except these ones, what would be the keyword for that? We'll call it overlap. Is that good? Okay, so so far we've learned the 9 extends the petal length. The 3 right here is always double. If it's an odd number, they overlap. If it's an even number, we can see them. Now, what's the difference between sines and cosines? So we're going to leave it again. Here's sine. That's what sine looks like. And you can see that sine actually has vertical axis symmetry. You can see that. Now, let's take a look at cosine in the same window and see if that's going on. Cosine of 3 theta. Oh, isn't that interesting? So sine theta had vertical axis symmetry. Cosine theta has horizontal axis symmetry. Now, what happens if I put a negative in front of these things? So I'll go ahead and put a negative in front, and all that's going to do is, yep, you can see that it's going to flip that over that vertical line, so it's going to go from the left first. So let's try it again here, see if this makes sense. Let's make that one a sine and go ahead and hit graph, and now you can see that it goes up like that. Awesome. So hope you learned some stuff about Rose curves right now. So these were our things. So one more time. This number right here gives you petal length. Cosine or sine. Cosine gives you horizontal line symmetry. Sine gives you vertical line symmetry. This number always doubles the petals, 2 times the petal length, where with cosine or with odd numbers, they overlap. And with even numbers, we can see them all. So hopefully you got a lot out of that, and play around with it. It's pretty cool, some of the graphs, and we know that we can change between radians and degrees. And hopefully, sounds like my neighbor just got their mowers out to do that. So hopefully that doesn't show up too much. Okay, so here we go. So now we're going to go to something called a Limousin curve. And a Limousin curve looks like this. It's got a plus or minus number. So we're going to put a constant out in front, and then we're going to add or subtract a number times cosine of a theta. And we're not going to do a 2 theta or 3 theta or 4 theta. We're just doing that. So here we go. Let's take a look. So let's start with 1. We're going to do 5 plus 2 cosine theta and 6. And it looks just like that, 5 plus 2 cosine theta. And you're like, what's going on? Why does that work out the way it does? And if you count on your boxes right here, you can see that it goes all the way to 5 up and 5 down. Maybe that's where that 5 comes into play. And then this goes to 3, but this goes all the way out here to 7. So why 3 and why 7? Well, the difference is on this one, if we're doing 5 plus 2 cosine theta, when cosine is negative 1, that becomes a negative 2, and 5 plus 2 is, or excuse me, 5 plus negative 2 would equal 3. And when cosine is positive 1, or at 0 degrees, you would see that 5 plus 2 equals 7. So they can go from a small part of 3 to a big part of 7. Cool. So what happens if I make this minus right in here? And what does that look like? Well, it does the same thing on the other side, and hopefully that makes sense. Now it starts off with 0, right, giving you a value of 3, and so on. So the next thing we're going to look at is, because we're going to discuss symmetry and the max and the mins, just like this. Let's try one like this. Let's do 2 plus cosine theta, where now I made the b value bigger and the a value smaller. So clear that out, and 2 plus 5 cosine theta. Give you a chance to be able to type that in. And again, pause this video anytime as you're playing around with this stuff, and go ahead and hit graph. And you're going to be, what? Whoa. So now it's got a little inner part of it. So why do we have this inner part, this little, kind of looks like a lime, and this is what I use, bad joke, right? This is called a Limousin. There's no H in this one. Limousin curve. And kind of like a, first 4 letters is Lima or Lima. Think of a lima bean. If you take a look at a picture of a lima bean, it's got that inner part like that. And why does that inner part occur? Okay, well, it occurs because the first number is smaller. And you can see, again, this will go all the way out to 7. This will go out to 3. So then what I want you to do is this. Let's do 3 plus 9 cosine theta. And I want you to think to yourself, oh, so 3 plus 9 should mean that it goes out to a total of 12, right? And maybe the inner part's going to go, that little bean in the middle is going to go all the way to 6. So let's try that, see if it actually does do that. So 3 plus 9 cosine theta, and hit graph. And look at that. It did exactly what we thought it was going to do. Okay. So I think you understand how these two numbers come into play on this. And if you actually typed in or plugged in values, and you can do that one at a time, plug in values. So when cosine 0 degrees, you know that's 1, so that gives me a 7. Cosine is 30 degrees, and again, that's going to give you root 3 over 2, and multiplied by 2, and times by 5. That's telling you how far out, right? How far out. Let me do this right here. When you're at 30 degrees, right? How far out do you need to go is whatever that value is. So if I go to my home screen, right now I'm on degree mode, right? Go to my home screen. I do 5 plus 2 cosine 30 degrees. I know that I'm going to get 6.73, so that means at 30-degree angles I'm going to go out to 6.73. Well, remember, at 0 is at 7, and that's why it's curving like that as it goes up. And then as it keeps going through, right, some of the times it's going to go all the way out here. Some of the times it's going to go here. And it's just based on those R values being positive and or negative when you plug in the values for cosine. Okay, so that graph, one more time, that's called a Limousin curve, and it's A plus or minus B cosine theta, and looks just like that. The only thing I didn't talk about, and I'll do one of these right now, is you should have noticed that all of those ones were horizontally symmetrical. So if I plug in a sine, I do the same thing again. Now you can see that sine has the exact same properties as cosine, except sine graphs are have a vertical line of symmetry with them. Okay, so clear. So the next word we're going to look at is what happens if you get r equals 4. Well, before I go ahead and graph it, I just want you to think about it. So, do you see a theta in this at all? And the answer is there's no theta in there. So if there's no theta in there, then all I have to do is I have to go, okay, well, let's check this out. So with 0 degrees, I get a value of 4. At 5 degrees, I get a value of 4. At 30 degrees or 45 degrees, I get a value of 4. At 70 degrees, I get a value of 4. At 90 degrees, I get a value of 4, because every time it's a value of 4. So I'm hoping that this makes sense, that if I just type in r equals 4, I should get a circle. Probably the easiest way to be able to graph a circle. I just go ahead and type that in and hit graph, and you're like, whoa, it's a circle. And some of you are like, Mr. Bell, that's an ellipse. I can definitely see it is wider. So again, zoom 5, that's our square window, and now we can see this. And if I wanted to, I could go ahead and make this one an 8, and I could have it looking like that, right? And then y equals, and then make that a 6, and go ahead and have that one look like that. And I got these cool, it almost looks like a bullseye ring. Let's put in one more here. 2, and poof, and I get that. And they're like, oh wait, we did some other things earlier. Why don't I do one that looks like this? Why don't I do one that looks like 8 cosine 4 theta? Like that. And you're like, oh. So, and you can see how you can start designing all kinds of different things. And remember, if you don't like it like that, you can also go to your window, and instead of 7.5 degrees, well, again, we can put it at 15 degrees. And now we've got a different design. So if you guys could, for when you guys watch this, come up with some design. Give me a screenshot of it, send it in an email. I'll send it out on the Remind app so that everybody can see it and go, whoa, that's pretty cool. Okay. So if I was to do something like this, and I want to talk about some math behind it, not just the designs, even though I think the designs are pretty cool, I could say domain of this thing. So what's the domain of this? Well, the domain is the inputs, or the x's, so I can put in a theta of 30 degrees, or 45, or 75, or 90, or whatever. I could keep going around and around and around and around and around for that. So my domain would be all real numbers. And I want you to be careful with that, because some of you might think domain is the x's if you're thinking functional notation. But remember, this isn't a functional graph. This is an r and a theta, the two variables that we're using. So the theta, that's our input. that's what we're going to plug in, is any degrees that we want, and we can go from negative infinity degrees to positive infinity degrees, as long as we don't include infinity, right? Because that's really, it's not a number, it's a concept. Now range, we could definitely say, hey, that goes from negative 4 to 4 in terms of our stuff. Symmetry, this one happens to be perfectly symmetrical on the x-axis and on the y-axis. And continuity, there's no gaps or breaks or anything like this, so it is continuous. Now we could talk about all of these things, domains and range and symmetry and continuity, on any of the graphs that we did. Okay? Okay, so here we go. We're going to move on to this one. This one's 5 minus cosine 4 theta. And we're going to discuss the numbers of petals and the petal lengths. Okay? So numbers of petals and petal lengths. We have something like this. So let's go ahead and pull our calculator back up here. Unfortunately, we got to clear out all of these cool designs, whatever you might have done before. And again, we're going to do 5 minus cosine 4 theta. So 5 minus cosine of 4 theta. And go ahead and hit graph. Like, what the heck is that? Oh, I don't know what that looks like. That looks messed up. And this is where it becomes a little scary in terms of our graphs. Like, does it really look like that? Or is that because my gaps are 15 degrees? So let's make them 10 degrees and see if I get a little bit more symmetry. So I got that. And then I go, okay, let's see if I make it 5 degrees. Well, it looks like that. And each time when I go in here, I might get some different stuff on this. So let's go here. You can see that I really wanted to, I guess I missed that. I really wanted to insert a 7 on that, and I forgot to insert it. So 5 minus 7 cosine 4 theta. And now you're going to see that this inner thing might actually give me some more stuff. You're like, whoa, look at that. So how many petals do you see there? And some of you are going to say, well, there's 4 of them, right? 1, 2, 3, 4. But if I look really closely, that looks like there's some more stuff going on really small right in here. So let's go ahead and zoom in to in. And you can see that I actually have 4 little bitty petals and 4 really big petals. So how big are these little petals? Well, the little petals are length 2. And then the big petals, let's zoom back out again. The big petals go all the way out to here. I wonder what those are. So let's go ahead and hit trace. Let's see if I can get out there. Well, that shows me my x is 8.48 and my y is 8.48. So if my horizontal is 8.48, my vertical is 8.48, then I believe that's an isosceles triangle. So if I do 8.48 squared plus 8.48 squared, enter, and I raise that to the 1/2 power or square root that, you can see that I get 12. So my little petals were 2, and my big petals were 12. How does that come into play? Little petals 2. Well, that's the difference between these two numbers. 5 and 7 is 2. And big petals were 12. 5 and 7 is 12. And that makes sense. So when 4 theta, the cosine of 4 theta ends up being -1, then -1 times -7 would be +7, and 5 plus 7 would be 12. Awesome. And when cosine of 4 theta equals +1, then 5 minus 7 would be -2. And a -2 doesn't mean that I don't go a certain distance. That just means, remember again, when we're doing angles. So like if I had a 145 degree angle, or 135 degree angle, right? That's right over here. Right over there, 135 degrees, splitting that up, right? And my r is -2, I actually end up going that direction. So I could end up having that petal be right here for my 135 degrees. Okay? So again, just a reminder of how some of these R's work. So you can play around with that, and you can, by adding the positives or the negatives into that, you can get, again, different petal lengths. So let's make these numbers a little closer on this, so that one's closer to the other one's size. So I'm going to go to y equals n instead of 5. Let's make it 3. And if I do that, that means the little petal should be length 4 and the big petal should be length 11. And now you can see that those inner petals show up a little bit more. And make it even more different. Let's make it 5. You can see that. And we can do that. Now, if I wanted to, just a reminder again, if I do this as 6 theta, that should give me 12 total petals, right? That's pretty cool, huh? And again, if I want to clear them up, I want to make them a little bit sharper, I change that 5 to a smaller amount. Where if I put this at 20, you can now see it's just doing weird little gaps, right? Okay? And for those of you with the colored ones, you can change these colors to anything you want and do cool stuff with them. Okay, so that's the last thing for those ones. So I'm going to finish with this. There are really 4 different types of curves: Rose curves, Limousin curves, lemniscate curves, and Archimedes. So we've really talked about these ones a lot. I want to talk about these 2 right here and why they happen. So first off, a lemniscate curve is a constant times the square root of a trig angle. So let's go ahead and put that one in. So I got 8 times the square root of cosine 2 theta. Okay, everybody got that? Zoom 6. And you're like, oh, look at that. And okay, so here's my dumb joke with these ones. Lemniscate looks like a figure 8. And you can see that. So how many petals does this lemniscate have? Well, it has 2. And you're thinking to yourself, but wait, when we had a 2 theta before, aren't we supposed to get 4 of those petals? And the answer is, yeah, we're supposed to get 4 of these petals. So what's going on with this? Let's see what's going on. So when I hit trace, and this is first time you're going to see this, if I hit trace and I start going around, you can see that I'm right here and I'm still good. I'm back to the origin. But then when I hit 52.5 degrees, it says x equals, and it doesn't give me anything, and y equals, and it doesn't give me anything. And it's like, wait, what? I keep doing it at 60 degrees, it doesn't exist. 67.5 degrees, 75 degrees, 82.5 degrees, 90 degrees doesn't exist. None of these things exist until I get all the way back to 135, and poof, you can see it pop back up on my screen again. And you're like, well, why is it doing that? Well, I'm hoping this is obvious for you guys. That's because when I have those angles, let's go back here again where they don't exist, say 87.5 degrees, or 97.5 degrees. When I plug that into there, I'm getting a cosine of an angle that's in either this quadrant or in this quadrant. And what's the value of cosine in this quadrant or this quadrant? Well, it's negative. Well, how do you square root a negative? The answer is you don't. And that's why this thing looks like this. Normally it would have a petal up here and up here, except those values in that lemniscate curve are undefined. And that's the same reason why if I do it like this, and I change this to a sine, I hit graph, you can see that sine's going to occur here and here. And if I hit trace and I zoom around, you're going to see that there's a couple places right here. It's going to be good again, and then it's going to disappear again in this last range. Okay, so it's only going to be positive when sine's positive, or it's only going to show up when sine's positive because the square root of negative number is undefined. I could do the same thing here. If I went back and changed this to cosine and I made this a 4 theta and I hit graph, you can see that I show 4 of them. But if I trace around, you're going to actually find 4 other places that it's undefined at, or 4 other values for things. Okay, so last one, this is the one that I actually started with on this thing. This one's called an Archimedes spiral. So this one's kind of cool. So I'm going to go ahead and put this in here. I'm going to put in point, and let's clear this out. I'll blow this up right here so you guys can see this. Focus it up for you. I'm going to do 0.6 theta, and I'm going to hit graph. And you're going to go, Mr. Bells, that kind of sucks. I don't know what you're saying. That's really doesn't do me much good. So I'm going to go, okay, well, what about if I put it in radian mode and I hit enter instead of degree mode, because the graphs change. And you're like, oh, wait, that's kind of interesting going on like that. So I'm going to change my theta step. Let's change it to 2.5 and hit graph. You're like, whoa, that's pretty crazy when I do it like that. And you're like, well, why the heck's it doing that? I did change it, right? I changed my, let me go zoom 6 now. Oh, what is that? That's smoother. Because remember, just a second ago, we changed it into radians, but my window was set in terms of degrees. So now I hit zoom 6, so I'm now in radian mode right there. So what I'm going to try now is this, is I'm going to change my 6 to a 50. So I'm going to do a whole bunch of these ones. Change that to 0.1, negative 10 to 10, negative 10 to 10. So right now it's 0 to 50. So I'm actually going to plot like 500 of these things. I'm going to hit graph, and you're going to see, whoa, it kind of spiraled out there, didn't it? Now it might still be going independent, and you got to be careful because your calculator might graph for a really long time. It might go a long ways out. So why does it spiral? Well, it's going to keep making my R value bigger and bigger and bigger as it changes those angles. So as those angles go out, my R is getting bigger and bigger and bigger as I go around and around and around. So let's go ahead and zoom out and do the same thing again. And now you can see that this looks like what you saw at the beginning of the day today in your Archimedes spiral. And all I have to do to get more of these spirals, or if I want to change this a little bit, so this is my last thing I'm going to do. I'm going to go to R equals, I'm going to do 0.2 theta. I'm going to come over here on my calculator because I can do this. I'm going to hit enter. I'm going to change it to I'm going to change it to magenta. Yeah, sure. So change it to magenta, and I hit enter. That's okay. So I got that, and then on my window, instead of 50, I'm going to do 100, and now you can see it's just going to grow and grow and grow. Almost looks like a spirograph, right? And if I wanted to, I could put it at 400 and take that entire window up. So, okay. So hopefully, again, on this stuff, that you play around with it, you see some of these interesting polar curves, why they work. If you put in the theta values for them, you'll understand that the R is just reaching out for them. Hope this was entertaining for you. Again, do some cool designs. Send me something that we can share out. And everybody likes to see something from somebody else during these crazy times. So this is Mr. Bells. You guys take care. Section 6.5 on polar curves.